get started with section 7.8, inverse trig functions, meanings, notations, graphs, and calculations. This is a really important unit. Your tools, you should have your unit circle, calculator, compass, and your handout. As with any mathematics, learning is active. So you need to have your handout and be thinking about the questions as we go along. So I'm asking you to attempt this first, which means you can pause the video at any time to respond for yourself, write it down, or to share with a neighbor. What meanings, ideas, processes, or symbols come to mind when you hear inverse function? Inverse function. I really want you to think about that. So you might have had ideas like, I don't know, does the opposite? Or perhaps you thought about it geometrically, that when you have an inverse function, you can reflect it over the line y equals x. So whatever your function is over here, let's say you have a linear function, the inverse of that function will necessarily be a reflection over that line. So these functions f and g are inverses of each other. You might also think about inverse notation, right? It's really important that you take care to use proper notation with inverses. So the inverse of f, a function, is written f inverse, right? F inverse. That notation is important so that we don't get confused with other notation or ways of thinking. So in this topic, because we're talking about trig functions, we're specifically going to be introducing what are, right, here's kind of our big question. What are the inverse functions for sine of x, cosine of x, tangent of x? And because they're functions, we want to know something about their domain and their range. Right? So maybe this was your original idea, or maybe you also had ideas about reversing the process. A really useful metaphor for inverses along this reverse the process idea has to do with a function machine. So I happen to have a picture of a function machine somewhere here. I guess I could draw one for you. Essentially, it looks like this. If you have an input, you have this little machine right here. You think about it having an input and an output. That's a function. Sometimes in class, we've drawn it with diagrams like this, right? We have an input and we have an output. So if this is our function f, this is our function f, we take an input of x, we get an output of y. Likewise, these would be our x's, these would be our y's. So some folks think about the reverse process as inverses because essentially it reverses that function machine. So in the case of an inverse of f, f inverse, which again, just to be careful, f inverse is not the same as 1 over f, okay? F of x is a function. F inverse of x, in this case, is also a function, so we want to be careful with notation that we're doing it properly. In this case, we say that an inverse reverses the process because now the input becomes our y, the output becomes our x, right? So, in a sense, the function is reversed so that our input is y and our output is x. F inverse. Okay, so let's keep going. In the process, on your worksheet, I ask you again to attempt this first on the warm-up. It's really important that you attempt this first. So I'm going to slide these out of the way. And now ask you to think about this. How many solutions does this equation have? This equation, cosine theta equals negative 0.4. Well, we haven't quite introduced how to do that yet, have we? But maybe, since you have your calculator, you might try thinking about, you have this button on your calculator. I always check whenever I'm doing anything with trig functions to make sure I'm in radian mode. Okay. Let's see. I have this button called inverse cosine, second inverse cosine of negative 0.4. Now, why did I do that? Right? Maybe this is two strategies. Really, you're looking for two different strategies for answering this question. I want you to reproduce your work on your worksheet. So the question is cosine theta equals negative 0.4. I'm trying the reverse process because I know a fact that f of x, if I have f of x equals a number, like cosine of theta equals a number, I know that if I take f inverse of f of x, f inverse of a, then I get x equals f inverse of a. So I'm going to apply that reasoning here. You might think, right, back to a relationship that we know. You might think back to when we studied e to the x and ln x. Remember that e to the ln x is x, ln e to the x is also x. Those functions were inverses of each other. So we're applying a similar kind of reasoning here. All right, cos inverse of negative 0.4. It gave me a solution. So in this case, I can write down that solution. I'm going to use double arrows to go across. So I took the cosine, the inverse cosine of theta equal to the inverse cosine negative 0.4, which led me to theta is the inverse cosine of negative 0.4, or theta is approximately 1.982. Okay, well, that's one solution. I saw someone else make a solution like this. We've done this solving approach before, when we have two functions equal to each other, like 2x plus 4 equals negative x, for example, right? This is recalling. I can take y1 equal to 2x plus 4 and y2 equal to negative x, and I can graph them to look to see if there's a relationship to find all the values that make that equation true, which is essentially what I'm asking here in my original statement. Anytime you're asked to solve, what you're looking for is what value or values of theta make this equation true. So in this other example that I was showing you, right, these were examples of other inverses. Here's another example. We would look at a function like this, 2x plus 4 equals negative x, and we would look for that intersection point. So we know quite a bit about our cosine function. So in my y1, I can write cosine of x, and in y2, I can write negative 0.4. I'm going to choose a good window. I'm going to do one full revolution, or one period, 0 to 2 pi, every pi fourths. Maybe I'll just do pi halves for fun. I know cosine, I want to include the value of negative 4. I'm just going to go from negative 1 to 1 because I know that's the range of my cosine function. I'm going to scale it every 0.1 so that I can see the negative 0.4 on my graph. So I have an expectation before I graph about my cosine curve. And I might also remember, aha, notice here, right? This function has two solutions, right? Solutions are the x values that make this function true. So a second strategy, here was strategy 1, right? Here's strategy 1. And let's do strategy 2 right here. I had y1 equals cosine x, y2 equals negative 0.4, and my graph helped me discern that on one period of cosine, here's my x-axis and my y-axis, at negative 0.4, I'll use black to show y equals negative 0.4, I get two solutions, and I can approximate those solutions using the intersect feature of my calculator. I'll calculate intersection, and the first curve is in blue, the second curve is in red. I'm going to move a little bit closer to make that guess a little bit better. My first intersection point, this ordered pair, is 1.982, which isn't surprising, negative 0.4, right? This matches what I found in my first strategy. My second strategy, my second intersection, I'll do that same method again. Second, calculate intersection. First curve in blue, second curve in red. I'm going to guess. I'll move a little bit closer so that it gives my calculator a better approximation of where I want it to look for the solution. And it found a second intersection of 4.3008. I'll leave it at 4.3. Y equals negative 0.4. The ordered pair for that intersection point. So to me, my second strategy lends me to conclude that x equals 1.982 and x equals 4.3 are solutions to the equation cosine theta equals negative 0.4. Beautiful. Second strategy.